Today, we want to start describing one-dimensional curves in R2 and R3. Now we've got a lot of tools to describe curves in R2. We want to see if those can be adapted to describing one-dimensional curves in R3. So let's think about the tools that we have for describing curves in R2. Let's talk about some of the tools that we have for describing curves in R2. One is with a function. One of them is with a function. This has some problems. This has some limitations. One of the limitations here is that if we can't have one x value correspond to two different y values. That's when we don't have a function. So there's a limitation here. Each input can correspond to only one output. So one of the limitations here is that each input can correspond to only one output. So the limitation when we're describing curves with functions is that each input corresponds to only one output. The major example that we have here, or I don't know if this is the major example. This is the one that we're going to be using all day. So for today, it's the major example. Circle. We can't describe this entire circle with just one function in rectangular coordinates. Make a radius of 3. So to describe it, I would need two functions. Plus or minus the square root of 9 minus x squared. Or I can write x as two functions of y, plus or minus the square root of 9 minus y squared, where we have the right and left. But the problem is that we need two functions. In rectangular form. So that's a limitation in what we can describe using these using function notation. The reason that we do function notation is that it makes things a little bit simpler. If each input is only going to have one output, then we're going to have an easier time imagining what the function looks like. This particular one we can describe with polar coordinates. So if we use polar coordinates, then we will get a function, but it's not x is a function of y or r, x is a function of y or y is a function of x, and r is a function of theta. So the limitation here is that each input corresponds to only one output. The other problem with this particular notation is, or not, with this particular notation is that if we go up to a function of two variables, we no longer have a surface. So we have an expandability problem. So our limitation So our first limitation is just there in when we're trying to describe curves in R2, simple things like a circle. Another limitation has to do with scaling our function notation up. So the other limitation is that if we're writing function, one variable is a function of the other variable, then we're no longer describing a one-dimensional curve, we're describing a two-dimensional surface. So if z equals f of x, y, or the other two variations of that, we're describing a surface in R3, not a one-dimensional curve in R3. So our function notation is not going to work because we're trying to describe a one-dimensional curve in R3. We might describe our curves in R2 with an equation. So rather than specifying one variable as a function of the other, just specify a relationship between the two variables. So for example, our circle can be described as x squared plus y squared equals r squared, or in this case, x squared plus y squared equals 3 squared. That would describe the entire circle. It describes the x squared plus y squared equals 9 describes the entire circle, the top, the bottom, and so on. But we run into the same scaling up limitation. An equation of 3 variables, an equation in 3 variables is going to once again describe a surface in R3. So we'd still have our scaling limitation. If we have an equation in 3 variables, we are going to be describing a surface in R3. And we're trying to describe a one-dimensional curve in R3. So writing the equation eliminates each input corresponds to only one output limitation, but we still run into the scaling problem. Remember, we're trying to describe a one-dimensional curve in R3, not a two-dimensional surface in R3. So we have another way that we may or may not be familiar with. It works out to about probability about 50%. So the next thing that we have in describing curves is to describe the curve with parametric equations. So in this case, instead of having the variables related to each other, we write each variable independently as a function of some parameter. So rather than relating the variables to each other, we relate the variables to some independent parameter. Rather than tie the variables together in an equation or with a function, we define the variables independently of each other as functions of some independent variable we call a parameter. We define each as the function of some independent parameter. And now we can see why I picked the circle, because this is a parameterization that we are most likely to be familiar with. So rather than defining x as a function of y or y as a function of x, I say x is some function of the parameter t. So x of t is 3 cosine of t. And then I make y a function of that t as well. So y of t is equal to 3 sine t. Then I just need to tell people what values of t to plug in, or I could, in this case, say for all t, but let's just go around the circle one time. This does some other things for us. So we know that when t is equal to 0, we'll be at the point 3, 0. So down here is where t is equal to 0. And then when t goes up to pi over 2, we know we're going to be going around the circle to this point up here. And so the x coordinate will drop down to 0 as t goes from 0 to pi over 2. So this happens at t equals pi over 2. So one of the things that we get when we parameterize our curve is an orientation on our curve. And in this case, a starting point. So we can see from this, by defining this interval for t, we get a starting point. The other thing that we get is an orientation on the curve. The curve has direction. So our previous descriptions, when we have a function, it's all just there. Usually when it's graphed from left to right. That's just because the computer is plugging in the values on the left and plugging in the values on the right. It's always just there. Here, we can imagine some parameter t, like time, where we have a beginning, a direction, and an end. So we get a starting point and we get an orientation. The curve has direction. In the context of what we're trying to do, what we're going to want to do with this, I want to describe some path in three-dimensional space. I want to know how that path interacts with the vector field. So I want to know what direction the curve is going at any point, so I can see how that interacts with the vector field at all those points. Any questions? Benefit of doing it this way, of parameterizing our equation, parameterizing our curve, is that we can scale this up. This doesn't have that limitation of scaling. When we add another variable, I'm still just making a one-dimensional curve. If we define a curve this way, I can just add on another variable. So by adding this third function, I'm still describing a bunch of points. Each value of t corresponds to still only one point. Each value of t corresponds to only one point. So once we plug in all the values of t, we will have a one-dimensional curve in R3. And that was our goal. Moreover, from the top view, we see we get the same top view. If I just look directly down from the top, it will look the same. I'll just draw this coming out 3D style. So it starts off at 3, 0, when t is equal to 0. I go around and I go up, and then I go up some more, then I go up, and then I keep going up. It's hard to do in 3D. So up, and around, and then around, and around. It was hard to see on camera because the z-axis is coming directly at the camera. So, and I didn't tell you to bring all your 3D glasses today. So I can't have it like coming directly at you. In another 30 years, 3D movies are going to become a thing again. Because that's the way it goes. Like in the 50s, it's like, oh, in 3D. And everybody's like, oh, this is how movies are going to be from now on. Then it went away. And filmmakers are like, oh, this is a pain in the ass. Like, oh, yeah, forget it. Then in the 80s, hey, remember 3D movies? Like, oh, no. Well, we're going to do that. And everybody's like, oh, ooh, 3D movies. And you could tell that if a movie was a 3D movie because they go through great pains to have stuff fly at you, right? And then it's like pieces flying at you. So you go, ooh. And like all this in the 80s, we're like, oh, this is the way that movies are going to be from now on. And then it went away because everyone's like, well, this is kind of a pain in the ass. And then recently it's like, oh, no. Now this time, 3D movies for sure. And it was like, oh, ooh, ah. Was Avatar in 3D? Was Avatar in 3D? I don't even remember. I don't understand why this is such a big deal. Because it's like, I don't even remember if it was in 3D. But anyway, people are like, oh, ooh, ah. And then what happened? People are like, oh, man, even with computers, this is kind of a pain in the ass. So, I'm guessing in another 30 years or so, 2050 is like, oh, all right. This time for sure, 3D movies. Anyway, neither here nor there. So what we're getting is we're getting a spiral. Imagine just a spiral staircase going up. So the points we're going to have 3, 0, 0. That's in the XY plane. Then once we get around to, that's not even. Once we come around here, we'll be at 0, 3 in the XY plane, but this will be up higher at pi over 2. And then once we come around again, we'll be at -3, 0, but we'll be up higher still at pi. And then we come around a third time, or come around in between through the third quadrant, we'll be at 0, -3, and we'll be up higher still at 3 pi over 2. And then we'll be back to the starting point, 3, 0, and 2 pi, where this 3, 0, and 2 pi will be directly over this point. So we're going up, and we're going up some more. And we have an orientation. From the top view, we don't see the increase in elevation. If we look at it from the side, so here we had x coordinate or x-axis and y-axis. If we look at it from the side, and with the xy plane, if we look at it from the side, let's say from the negative y-axis, we can watch the spiral staircase go up. If we just look at x and z and take out the y, then x is 3 cosine t, and z is just a t. And so that's why we get this cosine graph. And if we look at it from the side with the y, we can see the spiral staircase spiraling up. So the points that we're looking at here, this is the point 3, 0, 0, and directly above it will be the point 3, 0, 2 pi. Down here will be the point x is -3, y is 0, and pi. From this perspective, we're taking out the x and just looking at y and z. So this is still a point 3, 0, 0. We just don't see the changes in the x because we're looking from the positive x-axis. This would be the point -3, 0, pi. And here we are at the top, directly above where we started, at the point 3, 0, 2 pi. 2 pi units directly above where we started. So we get this spiral going up. The top view and the two side views. The view from the positive z-axis, the view from the positive y-axis, and the view from the positive x-axis. So parameterization is going to be the tool that we use to describe one-dimensional curves in three-dimensional space. This is the same parameterization that we used back in Calc 2 and back in Calc 1 and back in pre-calc, I presume, and trigonometry. That's the same parameterization where x and y are functions of t. It's just going to be more useful now because we can describe one-dimensional curves in three-dimensional space. In our previous classes, when we only had x and y, just those two variables, we did talk about parameterizing curves, but it was always a case of, why don't we just use functions? Why don't we just use equations? But now that we've gone up to describing one-dimensional curves in three-dimensional space, we're going to need our parameterization back. And so that's why it shows up and we have to deal with it in more detail. Any questions? Still has direction. It got a little bit squashed. I originally drew this. It was in California. Then there was an earthquake, so that's why it's a little bit bent. It should be fine though, structurally. I'm sure it'll be fine. Any questions? Comments? Slide a little more. All right. So we need to talk more about parameterized curves. That's going to be our project for this week. And then we'll see how we can make this interact with vector fields. But that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.